So hello everyone, welcome back. This is the lecture on model selection and estimation of generalization costs, and I will divide it into two parts. The first one gives you also some practical recipes, and the second one is a bit more theoretical. So the motivation here is that, particularly the second part is, can we get some understanding of how learning machines really work? And the first part is more what are practical methods to select the model which gives you the best performance. And because we have different choices, deep learning, neural networks, kernel systems, basis functions, linear systems, kernels, functions with different kernels. So which one gives you gives us really the best performance on the test data? Because we probably discussed already that the performance on the training data is not sufficient in general to tell you about the performance of the test data. So first we want to consider different costs. And so this is the notation we're using now. So we consider a function parameterized by parameters w or weights w. And we're considering the cost for one data point, for example. So sub means always on which data we are evaluating the cost. So here is one x and one y with a model with weights w. And we and others, we use the terms cost, loss, and error exchangeable. So we even if I sometimes call it cost, loss, or error, it doesn't mean anything different. So there's a quadratic cost, which is simply the difference between the target value y and the prediction of the model. And we take the difference and square the difference. And that's the cost which occurs at one data point. Then we have the misclassification cost. So here we assume the targets are -1 and 1. And this term is either 0 if it has the same sign, or it's 2. So magnitude is 2. So here we're essentially counting how often we are wrong. Or in this case, are we wrong in this one data point x and y? So if we have the same sign is the same as y, then this is no cost. Otherwise, a cost of 1. There's absolute deviation, which is the difference between y and the prediction. So it could also be 0 and 1. Y could also be 0 and 1, doesn't make a difference. And we take the magnitude of this difference. So it's very similar to the squared error. Essentially, it's the square root of this term. And sometimes it's considered more robust, and in particular, if you have outliers, outliers affect the least squares solution much more than a solution which uses this cost function. On the other hand, it's a little bit more difficult to deal with, but people are using that as well. Then there's a perception cost function minus y times f of x. On the positive part, we have Dropnik's optimal hyperplanes is 1 minus yf the positive, so we have here the 1 minus, here only the minus. There's a cross entropy cost function, which is the negative log of the probability of y given f of x, so it's a bracket missing. And can be applied to any log likelihood function, but for binary classification and logistic regression, it's the same thing as cross entropy cost. So this is or used to be at least a difference between machine learning and statistics. In statistics, one is often interested in the estimation of the value and the uncertainty of particular parameters. So we discussed this before. For example, is the parameter on the treatment W1 significantly non-zero. So does the treatment have an effect on outcome or not? In machine learning, one is more interested in the generalization cost, which is the average expected cost over all possible data for any fixed W. So it's written in this form. So it's a cost now. We are not just calculating the cost for one data point, but for all data points, which are randomly drawn from this distribution. So it's simply the integral of the cost for a particular data point, integrated over all possible data points, weighted by the probability that this data point occurs. Of course, in general, this p, x, and y is unknown. Otherwise, the problem would be very much simpler. So the typical assumption is that this distribution p of x and y is fixed but unknown, which, for example, also implies that the true f of x is fixed but unknown. At least in a frequentist approach. An estimator of the generalization cost is the average test set cost. So what are these test data? Test data are data we have available from the particular application, but these are data points we do not use in training. So we reserve them, don't touch them, and leave them to evaluate the model. Because when we evaluate the model on test data, so we write this here, this is a test data set, which is the average, so T is the number of test data points over the cost occurring on this data point for this learned W or any W. This is a so-called unbiased estimate of the test set error for any W, but not for, I mean, these data points cannot be used in training, so they have to be reserved and not touched. So this is a good thing, and it's unbiased. Error of estimate of the generalization costs for any fixed W, and we can compare different models based on the average test set performance. And this is actually what we are also doing. But of course, we are not doing it for any model, just for the for any W, but for the Ws which come out of the training procedure. Otherwise, this would be too costly, and we would generate some other problems. If we do too much testing, then yeah, at some point you might just by chance hit the test data and pick the wrong model again. So for if the variance or the uncertainty in this estimator goes to 0 if the number of data points in the test set goes to infinite. So, typically, you don't want to reserve a large set of available data as test data because you rather use them as training data. And a better alternative is cross-validation, which we describe a little bit later. So to obtain a better understanding of model performance, one is interested in the relationship between the average training set cost or error and the generalization cost. So, so this is how we write it. So this is the average training cost. So we average over all training data of the best parameter vector trained and evaluated on the training data in this form. So this is the cost at this data point xi, yi, and it's an element of this training data set of size n, divide by n, and we evaluate on the parameters which were optimized by training on this training data set. But then we, yeah, so this is, sorry, this is not average over train, this is the evaluation of our best parameters evaluated on the training data. So this is what we could call the training error. That's the example I said before. So this is just the average training error on the training data set. Yeah, and I also noticed that sometimes we're using train, sometimes we're using the letter D as a training data set. Here it seems to be more applicative to use the training data set. So this is just our training set error. So far we were interested in the generalization cost of a particular model with a particular best fit parameter, W hat training. Another quantity of interest is the generalization cost average over all possible training sets of size n, where the data set is generated from the same P of x, y. So, so in a way, it's simpler to talk about these averages than to talk about the performance of a trained model, particularly if you want to do a theoretical analysis. And it turns out that the training error underestimates the generalization error. So by this a little bit complicated equation, what we are doing is this is the cost of the training. So this is the the parameter we obtain in training, and we evaluate it also on the training set. Yeah, and this is the parameter optimized in training, but evaluated in the test set, or even the theoretical distribution P of x, y. And on average, this is larger than 0. So in other words, the training error is too small. It underestimates the test error. And we have seen this already in experiments or in the discussion before. As an expectation, the average training cost underestimates the generalization cost for the estimated W hat optimized on the training data. Thus, the performance of the trained model should not be evaluated on the training set, but on the test set, which is then an unbiased estimate of the generalization cost. Yeah, this equation is really the basis for the frequentist analysis of training and test error. We will discuss later. So, so this is a little bit preview on what we are discussing later. So consider the special case of models with fixed basis functions and least squares cost. So we have a least squares cost function, and let's assume the model is free of bias. So we don't have any regularization, or no, the model can in fact model the true function. So the true function is in the class of functions in the training data, considered as models. And so the models contain the true function. That's what I wanted to say. Then the generalization cost of the true model, the best possible model, and we're using the squared error here, is what we call a residual, or sometimes also simply called sigma square. So it's a variance in the noise. So as we discussed before, if at every instant nature adds some disturbance or some noise on the prediction, then it's impossible to predict that noise, and nothing we can do about it. So even the best possible model f of x. So if you have a model which perfectly matches f function f, we would have this residual error. So this is the noise essentially. The important thing is the expected generalization cost of the fitted model. So this is the model trained on the training data, but evaluated on the test data, and we take the expectation over all possible training data sets. So that's a little bit complicated expression over here. It's the sum of two terms. One is the residual, so sigma square, plus what will be called the variance. Yeah, this makes the training error larger than the residual. So this term is estimated by the average test set cost. This thing on the left side. An expectation is larger than the generalization cost of the best model of the best model by the term called the variance. You get expressions for that later. So if we change this, if we evaluate on the training data, the average training set, the expectation is residual minus the variance. So the difference between the training error and the test error. So this is the test error, this is the training error. The average over all possible training data sets is 2 times the variance in some cases, not all. But you get a little bit of feeling, no? So here's this picture for that. So we assume x is, comes from some p of x and y is f of x plus some noise. And then we generate these different training data sets as before. We do the estimate from training set 1 and training set L, and we assume L goes to infinite. Then, so this is the epsilon, the sigma square, then the average training error, so based on the estimates of the training set, will be smaller than the residual by the variance. So this will be residual minus variance, whereas the test set error of the models which are considered here will be the residual plus the variance, and the difference between training and test set performance will be two times the variance. And so the generalization error is larger than the test set error, and somewhere in the mean is in the middle is the performance of the best possible model. In the case we don't have bias. If it's bias, it's a little bit more complicated. So this was already a little bit theory, but let's now get to the practical side of things first. And so the practical task is we have different experiments, different models we have tried to get different results. Which one is really the best one on new data, on the test data? So this procedure can be applied if we have a huge number of available data. So it's a green rectangle over here. We simply split it into training data and test data and train our model on the training data in any way we want. And when we're happy and finished with training our model, we see what the performance is on the test data. And this is pretty simple, and we didn't used to do this for a while, but in the area of deep learning, this is in fact quite common, because just training one model can already take days and days. And then when you would repeat this procedure as a cross-validation, it will take a huge amount of time. So, so this is described over here. It's very simple. Um, so, so we do whatever we want on the training data, maybe with 10 different models. Nothing should be overdone. If you go to an infinite number of models, then at some point, just by chance, it will give you good performance on test data. So the limitations, so maybe 10 or 20 models, whatever. You look at the performance of the test data, and then you get an estimate of how well these models are performing on the test data, and maybe pick the best one. So, so this is describing cross-validation, but it's very easier to also look at the graphics. Oops, yeah. So, so this is the whole training data set available, and each time, so this would be 5 times cross-validation, we take 1/5 of the data randomly chosen. So no, we should first maybe scramble the order of the data, but afterwards we should not do a random selection anymore. So we first maybe mix up the data by scrambling the order, and then we take the first fifth of the data and reserve this for testing and take 4/5 for training. So that's nice, we have a lot of training data and only leave out a little bit for the testing. And then each time we take a different part of the training data for testing. So we do another experiment where we take this part for testing and the blue one again for training, and so on. So we do that 5 times, and each time another data set is used for testing. If you do it this way, that's a clean way of doing it. And you have 5 experiments, or maybe 10 or 20. You should also not overdo it. 20 is probably already large. Then you can get a mean and also a variance on your test set performance, because you have 5 times estimates about your test set performance. And another advantage is you're using a lot of data for training. And yeah, so you have different folds, and for each fold you get you estimate a parameter vector, and then the estimated generalization cost is just the average of these different training data sets. And then you can also look at the uncertainty in your prediction. So you take the difference between the test set performance of your model and subtract the mean and take the square and sum over all the different experiments, and then you divide by k and k minus 1. So you can, because we're interested in the estimate of the mean, we're not primarily interested in the distribution of the variance here. So that's why we can divide by k and k minus 1, which gives you the uncertainty of your mean estimate. And so we have not just the mean value of the test set performance, but also some degree of uncertainty. And if we have 2 methods, and this mean performance of the first one plus the square root of the variance we get for this model is smaller than the other model minus this. So in other words, the standard deviations don't overlap. So the mean of the standard deviation is smaller than the mean minus the standard deviation of the other model, which means that these error bars don't overlap. Then we can say, okay, this model gives you better performance in MJ. And this is what we are typically doing, and hopefully we don't see any overlaps in the error bars. Now the error bars are the square root of the variance. But sometimes it's not enough. We see overlap, and can we still show that one method is better than the other? And sort of the last straw is the paired test. So we don't look at the mean of the, we calculate the mean of the performance of the 2 methods. We evaluate the difference in the performance at each fold. So this is shown over here. So then we see a lot of variance in the performance. These are the different folds here. And we see a lot of uncertainty here. They are jumping around a lot. But each time the red one is better than the blue one. There's a smaller error. And if we just take the average of the red one and calculate its variance, and the average of the blue one and the variance, then they overlap. It's shown over here. But if we look at the difference, then the blue one is always worse than the red one. So we are simply analyzing the difference between the 2 models in the different folds. And if this value is significantly different from 0, we can draw conclusions here. And the advantage is the variance of the difference can be considerably smaller than the variance of x plus a variance of y. So maybe this is even highly correlated, then this goes to 0. So this is what we're using here. And if in classification problems or as an alternative, you can look at the Wilcoxon signed rank test, which does something similar. So this was the evaluation of the model after training, after everything is fixed. But sometimes we have these nuisance parameters or hyperparameters, which we also have to find. Well, essentially, we do a folded approach. We do this also that's shown over here. We take our training data, and in one of the folds we were considering, now we had some test data, maybe 1/5, and then the rest was training data. And training data again is split up into a larger set, which is used to optimize the W, and a smaller set on which we optimize the hyperparameter lambda. Yeah. So we can optimize hyperparameters, but they should be optimized within the data which we have reserved for training, and we should not look at the test data. And then we can do it for every fold and get the same stuff. And then at the end, we have maybe also a good idea of what the lambda is, the hyperparameter. In this case, we assumed, for example, a hyperparameter lambda. And this is a curve we will discuss in the second part in more detail. So there is something like model complexity here on the x-axis. So these are simple models. These are complicated models. And I think we discussed this already when we just talked about stop training. So if you allow your model to become more and more complex, the prediction error or the cost becomes less and less, and might even become zero. If you have a complex enough model, all the data can be fitted and it looks perfect in the training data. But that's why you need to look at the test data, because the test data might increase at some point. So if your model complexity becomes too high, you might see an increase in the test set error. That's why it's so important to look at the test data. And then maybe you decide that this is the best model for you with this complexity, and that this is too complex. This effect is also called overfitting, because one intuition is that you start fitting the noise in the model, not the structure in the model. Yeah, there's how do you search for hyperparameters? So if you only have one, you might, or two, maybe you do a grid search. You pick a reasonable range and try a number of options. But this becomes problematic if you have many hyperparameters. And it turns out a pretty good approach, a very simple approach, fortunately, is just to do random parameter searches. So you don't try anything fancy, but in the range. So let's say you have 10 parameters. You simply pick whatever, 20, 30, 40, 50 different random selections from these hyperparameters in this 10-dimensional space, and work with them. And smarter approaches often don't work very well. And the explanation people have found, let's say you're playing with 10 parameters, but 9 of them are really not really very important, how you pick them. And only one of them is important. And if you do random choice, you are exploring this one dimension quite nicely. Whereas if you do something smart, maybe you move in this 10-dimensional space, and this one dimension, which is really important, is not really explored a lot. But it's definitely also an ongoing area of research. People are not at the end here, and people are probably trying more and more fancy things in the future. So this is the first part, and we will continue with the second part in a moment.